Hello everyone, my name is Trenton, and I am an undergraduate student in the software engineering program at Thompson Rivers University in Kamloops, British Columbia, Canada. Today I will present fuzzy logic tuning for a nonlinear pose filter, where the membership functions of the fuzzy logic controller are optimally tuned using the gravitational search algorithm. In today's outline, we will start with an introduction where we will introduce the pose problem, and you will see that it is an essential task in the majority of robotics applications. Next, we will move to the problem statement and formulation of the pose problem. Then we will consider the proposed filter strategy, which is divided into two parts: the gravitational search algorithm and optimal fuzzy tuning for the nonlinear pose filter. Following that, we will show the obtained results, and finally end with a summary. The pose problem is considered to be a major subtask in a majority of robotics applications, in particular, automated and semi-automated applications. We can see it heavily in unmanned aerial vehicles, underwater vehicles, as well as ground vehicles, and many other applications. Our objective with this application is to end with a successful control process. However, the successful control process relies on the true value of pose. Unfortunately, it is difficult to obtain the true value of pose because normally the pose information is obtained through a set of sensor measurements, which are typically uncertain because they are normally corrupted with noise and bias components. The objective is to build a pose estimator to estimate the value of pose, such that the estimation is very close to the true value in order to end with the successful control process. So the equation of motion of any rigid body rotating and moving in 3D space can be represented by equation 1, where r denotes the body's orientation, p denotes the rigid body's position in 3D space, omega represents the rigid body's angular velocity, and v represents the rigid body's translational velocity. As stated before, our objective is to estimate the value of the orientation of the rigid body in the 3D space and to estimate the position value of the rigid body in the 3D space. So, with an understanding of the necessity of pose information in the control process, we see that the controller requires R, or the rotational matrix of the rigid body, as well as P, or the position of the rigid body. As noted previously, we normally obtain the information for R and P through a set of sensor measurements, which then give RM and PM, which are the measurements of the orientation or rotational matrix and of position. Additionally, as said before, the measurements are normally uncertain, particularly if the measurements are obtained by low-cost measurement units. In this work, we are building a filter that will take the set of sensor measurements and produce R hat and P hat, such that hopefully R hat will be very close to R and P hat will be very close to P by the end of the process. Here is the pose problem of a rigid body rotating and moving in 3D space. Normally we will obtain the pose information through the combination of an inertial measurement unit and the vision unit. Here is the observer design. Our objective in this observer design is to optimize the value of k such that the value of k will be increasingly aggressive with large error, and k will be very small at small values of error. Now let's move to the proposed filter strategy. First, we start with the gravitational search algorithm. Here is the flowchart of the gravitational search algorithm. And now we move to the optimal fuzzy tuning of the nonlinear pose filter. We selected the following fuzzy rules according to the value of the error and the rate of change of the error. VL denotes very large, L denotes large, M is medium, S is small, and VS is very small. In order to use the gravitational search algorithm for the fuzzy tuning, we need a cost function. So we selected the following cost function, where it is divided into two parts: ETR, which is the transient value of error, and ESS, which is the steady state value of error. As we see here, the transient value of error is between 0 and 1 second, while the steady state value of error is between 4 and 14 seconds. This error is composed of two main components, which are the normalized value of the orientation and the normalized value of the position, and the weighing factor was selected based on a set of trials. Now let's go to the optimization. So our objective is to optimize the input membership function of the fuzzy logic control and the output membership function of the fuzzy logic control. For the input function, we have 11 parameters that we would like to optimize. They're K1, K2, all the way to K11. And this set of parameters are optimized according to these lower and upper bounds that were selected based on a set of trials. Here's the output membership function, and again, our objective is to optimize the following 11 parameters, K12, all the way to K22. Once more, the values of K are bounded between the set of constants on the left and the set of constants on the right, and we selected the sets of constants on the left and right based on trial and error. And then with the following proposed scheme. Tuning the value of K so that it is tuned based on the fuzzy logic control, and optimally tuning the input and output membership functions of the fuzzy logic control using the Gravitational Search Algorithm. Now let's move on to the results and discussion. First, we start with the measurements and initialization. Consider the following set of measurements. Omega m denotes a measurement of the angular velocity, and Vm denotes a measurement of the translational velocity. B omega and Bv are the bias, and n omega and nv are noise components. Next is the true value of the angular velocity and the true value of the translational velocity. Then the value of the bias and noise components. For inertial measurement units, we have Vi in the body frame equal to the true value plus bias and noise, such that the value of bias and noise are as given. For the landmark measurement, we have the landmark measurement equal to the true value plus bias and noise. For the set of initialization, in order to start with a large value of error in initialization, we selected the true value of pose to be equal to the identity matrix, while the estimate of pose is equal to this matrix, which is not equal to the identity. Here is the optimized input membership function. And here is the optimized output membership function. So now let's move on to the obtained results. Here is the orientation, and as said earlier, the error has started at a large value, and here is the error in position that also started at a large value. Both are regulated very close to zero, which was our objective. And here is the difference between the true value and estimate. The initial value started very far from the true value. Here, black refers to the true value of orientation, and blue denotes the estimate. We can see here the strong tracking capabilities of each of the three components of orientation. Phi, which is the roll angle, theta, which is the pitch angle, and epsi, which is the yaw angle. And here we can see the strong tracking capabilities for the position in the 3D space. Once again, we started with a large value of error for the x component, y component, and z component. And again, this figure shows strong tracking capabilities for the three position components. So to conclude, a nonlinear pose filter is proposed. And this proposed approach is able to tune the adaptation gain online, with numerical results showing the fast convergence of the pose error from very large values to very close to zero. Thank you for being part of this presentation.